Hello everyone, welcome back to grade 11 physics. This is our last actual um, lesson for the year. We're going to talk about the motor principle. So this is the last thing we're going to talk about. We're going to extend what we just learned about with the right hand rule into something useful, which is a motor. So how does an electrical, well in this case an electrical DC motor work? So just a quick review of the right hand rule so far. So if we have a current that travels through a conductor and we have a uniform magnetic field, right, it'll feel a force which is at right angles to both the direction of the magnetic field, so in this case these are these lines here, and the current. So the way in which we have a vector that's perpendicular to both these two vectors, the magnetic field vector, we got our magnetic field going this way, and we have our current, we can make it a vector going this way. Right, so we have that vector and this vector. So our force is then going to have to come out of our palm, as we showed in the last video. So what happens now if I take a wire and I just put it between some magnets? According to my right-hand rule, I'm going to get a force, in this case, up. So I can attempt to try to you know show you how this would work with my right hand, but it hurts my brain. Okay, let's just leave that for now. You can go back to lesson 5 to play with that if you want. But right now with your hand, so take your hand, your fingers are going to go that way, your thumb, and the force will come vertical. Okay, so what I'm going to do now is I'm going to take that wire. Oh, and again, if you go the other direction, it's going to go down. So if I take this wire now, and instead of just having one wire, I loop it around. So I have two different currents. I have a current going up and a current going down. So what's going to happen is the one wire is going to end up generating a current, a force upwards. So that's going to want to pull that wire up. But the other wire is going to get the force in the opposite direction, which is going to want to pull the right-hand wire down. So what's going to happen in this situation? We're going to end up with a torque. We're going to end up with it wanting to spin. Torque is just a force in an angular direction. A force around in a circle is basically a torque. So this is going to want to spin my wire. So if I let this freely spin, let's say I put it on some sort of an axle, some sort of rotary device, and I let it spin, it's eventually going to end up vertical. And in this case, we're going to end up with those exact same forces are going to be there, but now they're going to be opposing each other. And in that case, they're going to cancel. But since it was rotating, there's going to have some inertia, right? We got it spinning originally. This was the original situation, right? We got it spinning. It's going to end up vertical, but then the inertia is going to make it continue on, and it's going to end up flipping the direction of the polarity. So we're going to end up with the force in the opposite direction and the torque in the opposite direction. Okay, so what we end up right now with in this situation, if we have it set up like this, just this loop in a uniform magnetic field, we're going to end up with this oscillatory behavior. It's going to want to flip-flop back and forth between those situations. And if there's any sort of friction or something, it'll continually lose energy and it'll end up in that vertical position. It'll end up in an equilibrium. Right? This is the equilibrium position. Any angle outside of that equilibrium position, any angle of rotation, is going to cause it to want to go back to this situation. So, is this a motor? Have we made a motor? Not really. This is going to be a pretty useless motor to us since it's not spinning. It's just wobbling back and forth and eventually reaching some equilibrium position. So not a particularly good motor. So what we want to be able to do is have it continually go around. So we want to, once it flips over, we want it to change the polarity so that it's always in the same situation. So this video here, this is what a motor looks like. A very, very simple DC motor. Okay, so as you can see here, what's happening, we have a battery producing a current, and that current goes up to these brushes, and this is providing a current through this loop. And notice what happens every time it does a full rotation, if you watch this arrow, it's flipping back and forth. So every time it does a full rotation, it's changing the polarity. It's changing the direction of the current flow in the wire. So there's a pull, and then once it gets to this point, it flips. So watch those green arrows. The green arrows are always pulling it around in a circle. So we've created a motor. So we're using our force on a wire in a magnetic field, force on a current, sorry, contained in a wire. And because of the way that these brushes, notice that there's this cylinder here, and it's split in half. This is what we call a commutator. The name of this thing is called a commutator. So it commutes the current. It flips it back and forth. So the current goes from one direction to the other. See how this is always, let's say this is positive, so this is always positive on this end, and this is always negative, which means that, if I can pause this for a second here. Let's see, can I pause it? No. Why isn't it letting me pause? Oh, so you can see how it continually is switching back and forth between the polarities, which is continually switching the direction of the force on the wire, which keeps it going around and around and around in a circle. Now, this is not what this is just a schematic diagram of what a motor looks like. This motor would not be a particularly effective motor because the force is maximal when the loop here is flat. There's hardly any force when it's up and down. So it would be very jumpy. It would be very difficult to get going because it always wants to sit in that equilibrium position. Sorry, it would have maximal force, when the wire is flat with respect to the magnetic field. So that would mean vertical, really, up and down. So it has no force when it's flat with respect to the ground. Get that? Okay, so it has maximal force on it when it's going vertical, when it's in the plane of the magnetic field lines, right? Those are magnetic field lines passing in between here. Now, so again, that's not going to be a very good motor since it's going to be very jerky. It's going to have a maximal force and then no force, and if I tried to rotate it, it would have it wouldn't be very good. We want to smooth it out. So a modern motor ends up looking like this, where there's quite a few differences in our schematic motor to what a modern DC motor would look like. First of all, the main big difference is you can see that the permanent magnets are actually electromagnets. The magnets that stay still. So in this picture, this magnet here, that's what we call the stator. It stays still, it's stationary. And instead of using like a magnet, we use an electromagnet. So you get a core, an iron core of some sort, a whole bunch of electric wire wrapped around them to generate a magnetic field between these. So we have two poles here. We'll have a north and a south here, and then a north and a south here. So we have two different magnets, fields. And then if you look on the rotor itself, instead of having one loop, you have lots and lots and lots of loops. And the commutator, instead of having only two sections, it has multiple sections. You can see all these different little levels. There's going to be some brushes attached. We call them brushes, things that allow the electricity to flow through it, and they're going to be touching, and then it's going to keep putting more and more electricity into these different rotors. And also, there's some interesting geometry that goes along with that, but that's way beyond our course here. So we have a rotor, and instead of having just one loop, we have many, 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 many loops in it. So we have lots and lots of different ways for the electricity to flow. Commutator split into a whole bunch, and field windings. So instead of using a stationary, a ferromagnetic magnet, something that has a constant magnetic field, you have a magnetic field that uses the same electricity that's used to turn the rotor. Okay, so this is what a modern DC motor would look like. And this just smooths it out, because it's, instead of it having just those the right, if there's a loop, there's just going to be the two. Now there's going to be a force all the time, and it's continually changing. There's going to be force on this loop, then the next loop, and then the next loop, and then the next loop, and the next loop, and the next, and it just smooths it all out. You get a lot more power as well, because of the multiple poles on the magnet, and multiple pushes on it. It keeps pushing it again and again and again, so it doesn't actually resist it as much. So you get much more power, as well as it just smooths out the motion. Okay. All right. So what I'd like you to do, just for to understand, this is more on the motor principle, uh, basically figuring out which way the wire is going to get pulled. Remember, the dot means coming out of the screen, the X means going into the screen. Okay. So just a couple questions here to finish, and then you're done all of the homework questions for the year. There's just a an assignment and a quick little a lab to work on to go through this. Okay? All right. So I hope you've had a great year, and I'll be talking to you later. Take care.